Okay, so we're going to try this again because earlier I tried to record this lecture and it said I didn't have a charged pen. So, this is lesson 33. We're going to talk about electrolysis, which is going to be our last lesson for chapter 17, and which will close up electrochemistry, and then we'll move into nucleochemistry. And so when we're talking about electrolysis, we are talking about a process which usually is the opposite of what everything we've been talking about, which is spontaneous processes. Now we're going to talk about processes which are non-spontaneous. But before that, we're going to cover just a little bit about corrosion. Okay, so corrosion is the deterioration of metals. So think of the things on the left-hand side of the periodic table. Okay, and they are going to be deteriorated by an electrochemical process. So electrons are being exchanged in some way, and when that happens, the metal deteriorates, and we call that corrosion. So some examples of corrosion, well, if you are a car owner, or maybe you own a bicycle, or anything made out of metal that has a paint job, you may know that when your paint job gets nicked and the metal gets exposed, that there runs a risk for rust to occur. Okay, so the element that's rusting here is iron, and it goes to iron oxide. Okay, so iron oxide, oddly enough, is the same red that we have here in East Texas, the dirt. So we have a lot of iron in our soil, and because of the oxygen, it's been corroded into iron oxide. And if you've ever seen a really old vehicle that's been left out to rot, or any iron implement, eventually it'll rust so that you can have holes, huge holes where the iron used to be, but now the iron oxide formed and then crumbled away and fell to the ground. So some other examples, if you've ever known anybody to own silver, silver undergoes a process that's called tarnishing. So back in the day, people used to get real silverware, and hence where the name came from. And you didn't store it in a cabinet; you store it wrapped in fabric to keep it from tarnishing, and it had to be polished. Nowadays, we buy silverware that is still made out of some sort of metal, but it has a coat, and it's not made out of silver, even though we still call it silverware. Jewelry can do the same thing. If you have a true piece of silver, not white gold, then it will tarnish over time, and it has to be cleaned. And then another one that's pretty common that people see is the blue-green patina to copper. So a few of you may know that the Statue of Liberty was a gift from France. Well, hopefully all of you know that. Way back when, and it was kind of a gift of friendship, of peace, of times of goodwill and working with other countries. And the Statue of Liberty is made out of copper, and so at one point, Lady Liberty would have been a copper statue. But the fact that she's that blue-green, that's actually the patina that results after the corrosion of copper. And in order to clean the Statue of Liberty, to return her to her copper state, would one, cost a lot of money, and would just be plain silly because the patina would just return. So it's not a process that's very easy to stop. Most of the time, the way you stop it is by coating the metal object with paint or something that prevents it from being oxidized. And we'll talk about some other things that promote the process of corrosion. So rust is a very common example of corrosion. It's probably the one that people know the most about. And so what must be present for rust to occur? Well, there's two things. One is oxygen, so this is O2, diatomic oxygen, and water. And so this can be in the form of water vapor, which when you live in a place like East Texas or anywhere along the Gulf or anywhere around a body of water, you're going to have a higher level of humidity, which means a higher level of water vapor. So the way that this works is, say that this is your metal object right here, whatever it is made out of iron. And eventually, or at one point, you may have had a thing of paint. Okay, and so the paint was protecting this iron object or a coat of another metal that doesn't corrode or oxidize easily. Now, say that one day, eventually, you have a chip in your paint, and the only paint part that's protected is the part that's here in blue. And you have this area right here, which is iron 3, or sorry, iron solid. Shh. That's the large Smith version coming in here singing. The little one is laying on the couch being quiet, and the large one's walking around singing. He's okay. Okay, so say you take a chip out of your paint, you have your iron solid right here. You have oxygen, you have water, both of which are components in the air. And then you have this reaction right here. And the anode reaction is going to be iron solid going to iron 2 plus, which loses 2 electrons. So let's write this out here. Iron solid goes to iron 2 plus 2 electrons. Okay. Then there's going to be this other process that occurs, which is iron 2 plus further oxidizes into iron 3 plus. And then our cathode is going to be what's occurring between the oxygen and we have the formation of water. Okay, so now what ultimately ends up forming when we have rust is Fe2O3. So even though it does proceed by the oxidation first to iron 2 plus, that iron 2 plus is going to oxidize further into iron 3 plus, which is the compound that we associate with rust. Iron 3 oxide. And you can buy this stuff, and that's amazing because it's everywhere out here. Okay? All right, so the next question says, why does rusting happen so much faster in the presence of salt water? And the reason why is because salt water has more hydrogens. Oh, I'm sorry, more ions. I don't know why I have hydrogen stuck in my head. Because it's more conductive. It has free ions. Okay? Most of the free ions are going to be things like Na and Cl. Those are the two major components of salt water. But there are other ions available. Okay? So if you've ever... it's kind of a problem whenever they sand the roads, or not sand, salt the roads for ice, and you drive your car, and if you live in a place where they do that a lot, you'll typically worry about cleaning out the undercarriage of the car to make sure, going through a car wash or something similar to wash off the salt, because if the salt stays on the undercarriage, on all those metal components, eventually what can happen is it'll rust. And so it's not something we see so much here in Texas, even though it does snow or ice. It's because it doesn't do it enough to do a lot of damage to the car, but it is something that does happen as a result of the salt and the ice water mixing together. Aluminum oxidizes much more easily than iron. So why don't aluminum airplanes and soda cans corrode? And so for the most part, the reason why is because they go ahead and they take this step, and let me write that so it looks like aluminum, and they essentially, this is the process in which aluminum would rust, if you called it rust, in the presence of oxygen, and it makes aluminum oxide in the presence of oxygen. And so essentially with airplanes, what they go ahead and do is they oxidize the aluminum beforehand and then use that material, which is much stronger, in the construction of airplanes and soda cans. And so this becomes a protective coating on the outside. So it looks like, say that this is your soda can, and this does not look like a soda can. And they're going to oxidize this outer layer so that it is only aluminum oxide, which is very stable, makes it great, and it's very light material. And then everything else on the inside would be pure aluminum. So it's going to be surrounded by an aluminum oxide coating. Okay? And the thing is that the aluminum oxide is a very strong coating, where when iron's exposed to oxygen, it rusts and just basically corrodes away into a powder. So it's not a very good preventative measure. So the ways in which we try to prevent rusting is to paint the surface, so cars, bikes, things like that. Use an alloy of iron and something else. So stainless steel includes chromium. Passivation is creating a thin layer of the oxide on the surface metal. So this is what they do with the aluminum oxide. Coating the surface with another metal. So copper pennies have, it's kind of the opposite reasoning though, but copper pennies are actually a mixture of more than one metal. And so that's a cost measure, but it's an example of having a metal on top of another metal. And then zinc plating or galvanization is another example. So zinc plated metals are called galvanized because they are coated with something that oxidizes more readily. This causes the metal that's being protected to act as the cathode. It's also known as cathodic protection. So if we're looking at here, this example, magnesium here is acting as what's called the sacrificial, which that's not spelled right, not enough I's, the sacrificial anode, meaning it's going to undergo oxidation, and that protects the iron because the magnesium is going to oxidize and the iron is going to stay iron. And the reduction equation is going to be the oxygen forming water. But once this sacrificial anode runs out, well, then the iron might be more susceptible. But as long as the magnesium rod, the sacrificial anode, is around and they are connected, then it is not going to rust. They do similar things under the ocean where you have underwater pipes. They will have sacrificial anodes that are around to protect the pipe from undergoing oxidation by putting something on it or around it and near it that's bigger and better and more likely to oxidize, which then protects the pipes that we need to prevent from busting open. So let's talk about electrolysis. Electrolysis, zoom out, is the process by which electrical energy is used, okay? And it's going to be used to cause a non-spontaneous chemical reaction to occur. So when we talked about galvanic cells before, we did not necessarily specify at the time, but these were spontaneous processes only. They were always written in the forward direction, with the anode being what's likely to be oxidized and the cathode being what's likely to be reduced. And the electrolytic cell is going to be the apparatus that's used to carry it out, to carry out that non-spontaneous process. So, for example, if we're looking at this process right here, one thing I want to point out is that the electrolytic cell is going to be non-spontaneous. However, the electrons are still going to flow from anode to cathode. Okay, so we're not changing the direction of electron flow. You can still see it's left to right, but we're changing which was likely to be based on those standard reduction potentials. Because remember, the cathode, we said, was more likely to be these positive numbers, and the negative numbers were more likely to be the anode. And so we used the standard reduction potential values to predict cathode and anode, but now they're going to be the opposites. So here we have, it's kind of hard to see this all lined up, but we have liquid sodium and chlorine gas, sodium chloride, and molten NaCl. And so what they're doing here is they're bubbling in, or they're basically filling with NaCl, and then going ahead and capturing Cl2 gas by oxidizing it. So they're going to oxidize the chloride anions into diatomic chlorine gas, and then that's going to be captured by bubbling it out. And the sodium is going to be reduced into liquid sodium, which is pumped out the left and the right. Okay, so normally the way this works is you take solid sodium, bubble chlorine gas over it, and you form NaCl salt. In this case, so this is the spontaneous process, the way I have it written right here. This right here is the non-spontaneous. This is taking your sodium chloride that you formed and unforming it and returning it back to its elemental state. And that requires energy. Okay. So if we looked at it as far as the electrochemical cell setup would look like, you have your anode, your cathode, which we see here the iron is the cathode, and the anode is carbon. Electrons are still going to flow in the direction that they left to right, just what we said, but there is going to be a battery which is providing that electrical energy. Before, this was just a voltmeter. It was measuring the amount of voltage put out, but this is requiring a certain amount of voltage to happen. So in an electrolytic cell, the battery is used to drive the electrons from the anode to the cathode. And this is used to drive reactions that have a negative E cell knot value. So if you think back to the lab, you had a table and you had half cells, right? And you might have a negative or positive value here, and then it was negative over there, negative here, positive there. And so we saw that the numbers were the same in the two, hopefully, in the two cells. The only thing was one was positive, one was negative. One was spontaneous and one was non-spontaneous. So another example of of electrolysis is the electrolysis of water to form hydrogen and oxygen gases. I don't know why the image is way over here. So we have, in here, we have water, H2O, and you have the application of battery, you have an anode, a cathode, and then you are capturing hydrogen gas and oxygen gas in these inverted test tubes. And you can see the balanced chemical equation is right here. Okay, so this says, why is this done, this right here, done in a solution of H2SO4 instead of pure water? Well, what this does is this increases the concentration of the H plus ions. And the reason why that's important is because the oxidation and the reduction reactions are as follows. The oxidation is the formation of your oxygen, formation of 4 protons and 4 electrons, and the reduction is going to be the protons gaining the 2 electrons to form H2. And so the H2SO4 is a provider of the H pluses, which helps to drive the reaction a little bit faster than it would without. All right, so there are some important quantitative aspects about electrolysis. And so I'm going to go ahead and pause here and then pick up and then do this in a separate video so that they're a little bit easier to upload. So this is going to be 33 part 1, and make sure you watch 33 part